All right. Good afternoon. I'm Steve Werby, and I work at a company called Befriend. Before I get started, I'm going to tell you a couple of password cracking or password failure stories from my history. I've been working with password cracking for about 13 years, but the biggest problems I've had just really have to do with human failure. So about 13 years ago, I was doing some consulting work for an ISP/web hosting company that had a lot of religious sites as their clients, and I was asked to crack their passwords. So I used John the Ripper, and within about 1 second, I got almost all the passwords, and there were really only 2 passwords that these hundreds of sites used for their administrative passwords. Anyone want to take a guess what they were? That was actually that was on the list, but that wasn't in the top 2. Jesus and church. So almost every single one of the websites used Jesus and church. So fast forward about 10 years, I was at a large organization. We had a big problem with phishing. And so we did a lot of education. I was the Chief Information Security Officer. We did a lot of education to let people know what phishing was and how to avoid it. And I had a user, and that user responded to a phishing attack by sending their password via email to the attacker. And so their account was disabled, and then they called in the help desk, and it was re-enabled. A couple of days later, the same user's account also was victimized by a phisher. So I decided this time to call the user up because it was a large organization. We didn't do that the first time. So I called the user up and I asked, did you respond to a phishing attack? And he said no. So I thought, well, maybe somebody else was using the account. And I thought about some more and I asked the user, well, did you respond to an email requesting your password on Monday and Wednesday? And he said, well, yeah, I did that. But you guys were asking for the password because it claimed it was from our internal IT. So the moral of the story really is, no matter what technical controls you put in place, it's going to be the process and people failures that come back to bite you. And that's my rule 0 for you. Okay, so I have to cover the basics. As I said, I've been in the field since 1999. I've served as a CISO at 3 different organizations. A large university, then the largest state agency in Virginia, which is the Department of Corrections, where I learned a lot of cool things like how to fashion weapons out of paper. Basically, you turn it into a cone shape, you wet it, let it dry, and repeat a number of times, and it makes a really good weapon. And then because I'm a glutton for punishment, I went back and worked at a different university. And as of a couple of months ago, I resumed working for myself. I have some degrees and certs that I'm not going to go into. And I've been cracking passwords since the Unix epoch. Well, not exactly. And when I did, I was working with John the Ripper, and now I work with some different tools that I'll talk about. So my lawyers tell me I have to have a disclaimer, so this is my disclaimer. You don't read it from top to bottom. It actually goes across and spans the gentleman's head. Does anyone recognize who that is? Jackie Childs, very good. So he's not actually my lawyer, but it's a lawyer I respect quite a bit. Okay, so there's my real disclaimer. These are only my opinions and mine only. I'm not going to actually go through an agenda, but I'm going to let you read what I'm hoping you're going to take away from this presentation. And I should say that the goal of this presentation is not to prove that I'm an elite password cracker. In fact, I know there's some people here at Hack3rcon that are better at password cracking than I am. I really want to expose you to the utilization of Amazon EC2, some of the tools that I utilize, and the thought process I go through when cracking passwords. Okay, so I'm going to cover some of the basics. So what is a hash? It's a one-way function that takes an input string and outputs a string of a fixed length. There are plenty of hashing functions that many of you are probably familiar with. Some of the common ones are MD5, various versions of SHA, Bcrypt, and numerous others. If anyone is able to tell me what these 2 hashes convert to at any point this weekend, beer on me. At least for the first person who's able to tell me what those hashes convert to that are in the bottom right. They're not going to be that, well, they shouldn't be that hard to discover, but they are not Jesus and church. You're potentially on the right track, though. And I say that the hashes should be unique, but some of the hashing algorithms actually have collisions which means that more than one input value could translate to the same output hash. In terms of password cracking, that doesn't really make much difference. There are really two general processes that you can go through when performing password cracking. And the first one that I list is the primary one I'm going to talk about today. Step one is to enumerate candidate strings, and what I mean by that is taking a list of these strings that you want to convert via a hashing algorithm, and then match that hashing algorithm output with the hash that you're trying to essentially determine the plaintext counterpart to. So you take some strings, you convert them through a hashing algorithm, you look at the output, and you see if the hashing output matches any of the hashes that you want to decipher. The second option is to use pre-computation. You may have heard of something called rainbow tables, which is a version of that. What that involves is essentially doing all the pre-computation of the hashes of the candidate strings in advance, which can take up a tremendous amount of storage space, but as we know, storage space is relatively cheap these days. And so instead of doing the work as you go, you have these pre-computed tables. You simply take the hash that you want to determine the plain text of, and it looks it up in the pre-computation table to see if it exists within that particular file set or database. So you could have billions of pre-computed hashes and simply do a lookup that can just take a matter of seconds. So why would you want to do password cracking? Obviously, it can be a lot of fun. There are plenty of password files that have been leaked on the internet. You can take them, you can download them, and you can practice cracking them. But there's also more practical reasons you might want to do that. So a few of them are listed. One would be to gain intelligence about user behavior. Users do stupid things. So if you have a password policy, for example, that consists of an 8-character string made up of at least one uppercase letter, one lowercase letter, and one number, many people are going to capitalize the first character in that string, and they're going to save the number until the last character in the string. So if you look at leaked passwords in hash files and perform analysis on them, you can learn about the behavior of users in different environments that may teach you something about how users behave in your environment. You can also use it to analyze the password hashes in your own environment. That can be a little bit political. It may take a little bit of effort to convince the executive management in your organizations, if there is executive management, that there is value in cracking the passwords of existing users. So you really need to think that through before you pursue that. But for example, if you have a password policy that you believe is weak, it's really difficult to go to the CEO or the CIO and say, I believe this password policy is weak, and talk about some statistical information. It's not going to make a lot of sense to them. If you can show them from a practical perspective how easy it is to crack passwords in your environment, you may be able to make a better case for changing password expiration or increasing the minimum length of passwords or performing additional education of your users or whatever it is you think may provide value in your environment. And 2FA just means two-factor authentication. So these are some of the things that I've advocated for in the environments I've worked in, and I've had an easier time advocating for those changes if I actually had some raw, tangible data I could show the people that made those decisions. So from a mathematical perspective, there's really two variables that are important when it comes to determining how strong a password is going to be and how long it's going to take to crack a password or a set of passwords. Step one, or variable one, is the number of tests that need to be performed, and variable two is the amount of time it's going to take to perform either each individual test or each collection of tests. And I'm going to go into more detail about what that means from a mathematical perspective. Okay, so looking at the average number of tests, from a theoretical perspective, there's really two components. It's the character set, which is the full array of characters that are legitimate and allowed in a particular password, and the length of the password. So Some organizations may only allow lowercase letters or numbers, so their character sets will be smaller. That's pretty common in the banking industry, airline industry. It's very common for airlines like Delta to only have a PIN that's numeric and very short. So the character set is going to be very small. And if the length of the password is going to be pretty short, the total combination of strings that have to be enumerated is going to be very low. So I have a couple examples I show. One's an 8-character string made up of lowercase letters and numeric strings only. The mathematical equivalent of what that will take in terms of key space is 26 lowercase letters plus 10 numbers to the 8th power, which is roughly a key space of 8 trillion. And that sounds like a lot, but as we'll find later with modern computing power, it won't take that long to enumerate all 8 trillion potential passwords. A separate version I show is an 8-character alphanumeric password, so as an additional key space made up of 62 to the 8th characters versus 36 to the 8th. And so the key space increases from 3 trillion to 218 trillion. So it's a factor of about 70. Are there any questions at this point? If any of you have questions, feel free to jump in. We should have plenty of time. If not, we should have a few minutes at the end. Okay. So I haven't mentioned what assault is, but assault is something that can and should be used in conjunction with a hashing algorithm. It's a string that is either prepended or appended to the input string before it's run through the hashing algorithm. There's a number of values to doing that. So with pre-computation tables, if a salt is used, and a salt could be a single character like the letter A through the letter Z, which would increase the key space by a factor of 26, or it can and should be something much longer, like a string that is made up of 8 characters that are completely random. Well, if you have a pre-computation table and have a salt, the amount of storage space required is going to increase exponentially. And as we see when we crack passwords, if there are numerous people that have the same password in the hash file, if there is no salt, everybody with the same password is going to have the same hash. If a salt's used, then theoretically everybody with the same password will end up with a different hash. So it'll make it much more difficult and time-consuming to crack those users' passwords. Moving on to the time it takes per test, it makes a big difference which hashing algorithms used. Some hashing algorithms are extremely fast, which may sound like a good thing. And it's a good thing if you're trying to crack passwords. If you're a black hat, that's great. If you're a white hat and you want to prevent people from cracking your passwords, that's bad. Now, older hardware is obviously going to crack passwords at a slower rate than new hardware. CPUs are much slower than GPUs, which are graphical processing units. And I'm going to be explaining how those can be utilized both with and without using Amazon EC2. And there's different software that can be used for cracking passwords, and some of them perform at a higher rate than other pieces of software. Okay, just to give some examples of different hashing algorithms and the relative rate at which they can be cracked. SHA-512, let's say we assign that a variable x. NTLM is about 60 times faster to generate an NTLM hash than it is for SHA-512. So if you want to be vigilant and make it more difficult for an attacker to guess your passwords, you want to use a hashing algorithm that's slower. Are any of you users of these sites? Okay, no one wants to admit that they're users of eHarmony, I get it. But I guarantee there's plenty of people in here that use these sites. All these are sites that have had, they're either their plaintext passwords or their hashes exposed via the public internet over the last few years, most of them within the last year. RockYou, I believe, was in 2009. The interesting thing with RockYou is that it wasn't actually the hashes that were published, it was the plaintext passwords, and the reason why is that RockYou was not storing hashes of passwords. They were actually storing the plaintext passwords in their password database. It's also different than the other three that I have listed in that with RockYou, the passwords that were exposed were not unique, meaning that if 100,000 people had the same password, there were 100,000 lines listing that same password. So it was able to give white hat hackers better information about the password frequency within the RockYou database. If memory serves me, the most popular password in the RockYou system was 123456, and I believe it appeared somewhere around 150,000 times out of 30, I have the number right there, 33 million password combinations. So I could have chosen any of these databases that were exposed for performing my testing. I chose to use eHarmony for no real particular reason other than that was the one that was most interesting to me. And so all these passwords and hash files were initially posted on web forums and or via torrents, and most or all of them should still be accessible. If you want to be vigilant, this is a bit of an exaggeration, but I would make the assumption that eventually your password database is going to be exposed. So whether it's exposed to somebody externally or somebody malicious or curious within your internal environment, it's best to assume that it's not actually a secret. So with the eHarmony database, there were 1.5 million passwords. I chose to just look at the first 1 million just to keep the numbers round. The last 500,000 passwords that I did not look at would not be expected to behave any differently than the first million. And these were all unsalted MD5, so no salt was used in the generation of these hashes. And this is a pretty large database. I'm going to make the assumption that most of you work for organizations that don't have password databases of quite this magnitude. But we'll see that it doesn't really make much difference in terms of the methodology. Tools that I have used on a regular basis include John the Ripper, a few versions of Hashcat, and CryptoA's multiforcer. There are a few versions of Hashcat, the traditional versions designed for running on CPUs, the plus versions designed for running on GPUs, and having an input file that consists of multiple hashes. So an input file that has more than one hash in it, one per line. Hashcat Lite is a specialized version of Hashcat to run on GPUs. It's designed to only process a single hash file. So that's not quite as practical, though there are scenarios where you may want to actually only try to crack one password hash. It is not a situation that is all that common. When you make last-minute tweaks to a presentation, sometimes you end up with slides that are out of sequence. And I realized at the very beginning I was missing a slide. I thought maybe it just disappeared into the ether, but it apparently is in the middle of my slide deck. So here it is. So this should have been before my traditional intro. I was going to let you know that I got my start in computing working on one of these in 1980. That's when I started doing programming, though I was very, very, very young. It was programming, but you probably wouldn't call it very sophisticated programming by today's standards. So it's not actually this machine, but the testing that I initially did was on a pretty old laptop that belonged to a colleague of mine. And on that particular machine, we were able to crack 14,000 passwords per second using Hashcat. That may sound like a lot, but it's not really a lot. And when we look at some of the modern computing that we utilized, and GPU technology in particular, you'll see how ridiculously slow this actually is. Now, in 1999, that wouldn't have been too bad. And these numbers all relate to performing attacks against MD5 hashes, not other types of hashes. But in terms of raw numbers, that works out to 1.2 billion per day, which is a pretty big number. But on the 5-year-old laptop, I wasn't very pleased with its performance. So when we talked about an 8 alphanumeric character key space before, it would take 1,187 days on this particular laptop to enumerate that entire key space. So that's roughly 3 years. I don't know about you, but I don't have a laptop that I can afford to leave on for 3 years. And even if I did, I wouldn't trust it's going to stay on and perform this type of attack reliably. So that's pretty slow. Okay, so when cracking passwords, I had really 3 different major options to consider. One was to use existing hardware. As I said, I had a pretty slow laptop. I had some other devices too that weren't much faster. And I had some devices that weren't too bad, but I had to utilize them for other things, so I couldn't dedicate them to password cracking. I could build a cracking box, and there's plenty of people that have done that. It'll only run you a few $1,000s. Roughly speaking, to build a decent GPU-based cracking box, let's say it's going to cost you about $1,000 per box plus roughly $500 per GPU. Really depends on what GPU you decide to purchase. There's different GPUs that crack passwords at different rates. It's not really what they're designed for, right? They're designed for graphical intents purposes. It just so happens they work really well for cracking passwords. And then I could look at a cloud service provider. And I was most familiar with Amazon because I'd used the Amazon EC2 before for web hosting and some other purposes. I looked around a little bit to see what cloud service providers existed that had GPU-based machines. I think I only actually found one other provider, and that provider didn't have an hourly service, at least at the time. They had a service that was monthly, and so that was a little bit prohibitive for what I wanted to do. So I decided to go with Amazon EC2. That didn't prevent me from looking at building a cracking box, but I thought before I decided to spend thousands of dollars of my organization's money, I might as well spend a few dollars testing out Amazon EC2 and see how that worked. Okay, so if I was building my own box, as I mentioned, it would cost me a few $1,000s. I mean, it really depends. I could throw 8 GPUs in it and increase the cost by $4,000, but it's only going to perform about 8 times faster than a machine with 1 GPU in it. To do this, though, I need a beefy power supply. These types of machines suck up a lot of power. I need really good cooling and electrical supply. If I don't have that, the machine's not going to run at all or not run very well. The CPU and RAM are not very important for these types of purposes. So if you're building a machine, there's no real reason to max it out with the highest end CPU with multiple cores and a tremendous amount of RAM. And you probably, if you're going to build a machine, would probably want to put more than 1 GPU in it. But you could always start off with 1 GPU, and if you needed to, you could add additional GPUs as long as you had the right slots for doing that. But those are a lot of things you have to consider, and you have to consider whether you have space, whether you have time to order a machine like that, and whether you think you're going to use it often enough to justify the expense. So you may find that that money would be better served for other information security purposes. So as I'd mentioned, I'd used EC2 before. There's no capital investment. There's no upfront cost to utilize Amazon EC2. Anybody can do it. All that's required is an Amazon account. You can utilize the one you already have, or you can create a new one. It's on demand, meaning that you can turn it on and off as you need it. It's scalable, meaning that if you want to have more than 1 machine, and they have the machines available, you can purchase the services of additional machines. So if you want to crack passwords 10 times as fast, you could fire up 10 servers. And I like that they had an option that included a GPU-based machine, though it's not particularly well suited for password cracking. It's the only one they have available. And it doesn't do bad, it's just not going to perform as well as a machine you could build and buy on your own. Oh, and the best thing is, once you know what you're doing, or if you follow somebody else's instructions, it really only takes you about 3 minutes from the time you have an Amazon account through EC2 to the time you actually can have a server up and running. So the startup process is to create an Amazon Web Services account. from a high-level perspective, create an instance which is a server, and to install the software that you need, configure that software in the server, and then run the software. There's really not a lot that you need to do to run Hashcat Plus or CryptoHaze Multiforcer. I had to do a few things like upgrade some drivers, install some packages using Yum or whatever the installation packaging program was on the particular flavor of Linux I was using. I've not tested this on Windows, but Hashcat does run on Windows. It runs on Mac OS X as well. I prefer to use Linux. That's my operating system flavor of choice. And with Amazon, I fired up some Ubuntu machines, and I also used a specialized version of Amazon Linux, which is essentially based on Red Hat. So like I said, it only takes you about 3 minutes to do, and you'll have a machine up and running. I'm going to show you some screenshots of what it actually looks like for you to fire up an Amazon EC2 instance. This is the EC2 Console Dashboard. You can see at this point I actually have 2 running instances if you look at the right-hand side. But if I wanted to fire up an instance, I would simply click the Launch Instance button that's in the middle of the screen. It would take me to this screen, which presents me some pre-configured systems I can choose from. You can see what's highlighted here is an Ubuntu server. This is one of the boxes that I utilized in my testing. I would simply click on it, choose whether I want 64 or 32-bit. Sometimes it doesn't offer you the choice. I tend to opt for the 64-bit. I would next be taken to this screen where I'm able to choose a number of variables that I want to change, such as the shutdown behavior. That's pretty interesting because you can specify that automatically when you build the server, if you shut it down or the server shuts down unexpectedly, it's either going to shut down or terminate. The difference between the two, I should have asked this earlier, who's actually used Amazon EC2? Okay, great. So probably 20% of the people in the room, so that's good to know. So if you shut down a machine, you can restart it at a future point, and however you had it configured and whatever data was stored on it will still be there. So it's persistent between shutdowns and startups. If you terminate a machine, the data is all going to be gone. So you don't want to terminate a machine if you expect you're going to want to utilize the software on it or the data on it in the future. And you can set that up to behave in this way automatically from this screen. Let's see what else you can do. You can set a key pair for authentication. So if you don't want to log in via a password, you can utilize an SSH key, which is a methodology that I normally use. On the next screen, you can name the server. I named this particular one Yoda. You can specify the type on the right-hand side, which is essentially the type of virtual hardware that's going to be associated with that device. So there are different pre-configured types that are available. They differ in terms of the number of CPUs, the beefiness of the CPU, the amount of RAM, and some other variables. And then for the GPU machine, there's only actually one option, and I'll talk to you in detail about what the options are for that one. You can see you can also specify a geographic zone. So if for some reason you want the box to reside in Asia, at a data center with Amazon in Asia, you can do that. I almost always choose a data center that's on the East Coast of the United States. There's some slight price fluctuation between the data centers, but it's pretty nominal. And a really cool thing you can do, I don't actually show it on the screenshots, is under the Advanced Details tab, there's a section for I actually don't remember the title of it, but it's essentially startup scripts. You can paste in any commands you want to have run after the machine fires up. So if you want to have it download files, upgrade packages, install software, add users, or do anything else that you can automate, you can paste that script in the startup script section, and when the machine's built, it'll automatically perform those tasks. So the way I utilize that for password cracking is I pull in my hash files from a machine that I host those on, I pull in my dictionary files, and everything else I need to work with or I know needs to be done to the box so I don't have to do it manually. Okay, so once you complete that phase, you're taken to this screen which tells you that your instance is now launching. It only takes about a minute and a half from that point for your instance actually to be available. If you pop on over to this screen here, it lists at that particular time the instances I had available through my account. You can see in the state column, it tells you what the state is of that particular instance. So I had 3 servers that were running and 1 that was stopped. And you can see there are various types of servers I had set up at that point. The 2 in the middle that are labeled CG1.4x large are 2 that are GPU clusters. The T1.micro is actually a very low-powered free instance that Amazon has available. So if you just want to get your feet wet and want to test Amazon out, for 12 months you can actually use the T1 microservice both on Windows and on Linux at the same time. And the number of hours they give you essentially equates to around-the-clock usage. So you could have a Linux machine and a Windows machine running around the clock for 12 months just to test it out. And the pricing goes up from 0 from there. But there are some machines that are very, very inexpensive. And you can see by default it generates a host name in the middle of the screen towards the bottom. You can also associate a static IP address with a machine. It's not actually necessary when doing password cracking, though it can make it easier if you're going to have clusters of machines that are going to be working together, or if you want to do something like web hosting. Okay. In terms of the pricing, it's dependent on a number of variables, but the most important from a password cracking perspective is the type of system that you're going to have deployed. So a system that has a single CPU and very little RAM, it's going to be less expensive than a machine that has a couple of GPUs in it and 33.5 gigs of RAM. And data transfer, data storage, and a few other things make a difference, but when you're doing password cracking, you're not really transferring a lot of data. Your hash files are going to be probably in the megabytes of size, they're not going to be in the gigabytes. You're not going to be passing a lot of data back and forth like you might be doing something like with web hosting or something that's very database intensive, transferring data between systems. So from a password cracking perspective, you can really ignore that. There are 3 different purchasing options. The first is an on-demand service, meaning that if you want to fire up an EC2 instance for an hour, you can fire it up for an hour. If you want to run it for 24 hours, that's great, you can do that too. They charge you by the fractional hour, rounding up. So if you run it for 1 minute, you're going to pay for an hour. You run it for an hour and 1 minute, you're going to pay for 2 hours. They also have a reserve pricing option where you can pay a flat amount up front for an extended period of time, and then the amount you pay per hour is much, much lower. You'd want to do that if you want to do something like web hosting for a large website you know is going to be running for a long time. And they also have something really cool called spot pricing, which allows you to take advantage of excess capacity they may have for different types of equipment and bid on it and get it at a much lower hourly rate, though it's not guaranteed. All right, so for testing purposes, there were a few different systems that I built. I actually collaborated with a colleague of mine to build these. It was his machine that was Zelda, which was the laptop I talked about before. Didn't really have a cost. It was already paid for. Electricity wasn't going to cost us much anything. Yoda was a machine that was running Ubuntu through Amazon EC2, had almost 8 gigs of RAM and 4 EC2 compute units, which is a kind of nonsense term, but what that works out to is essentially a machine that was roughly 1 gigahertz. I think it was an Opteron processor, I believe, from roughly 2007. It's essentially Amazon's baseline, and they measure everything relative to that type of machine. So the Yoda machine is equivalent to the processing power of 4 of those machines from 2007. So it's not super beefy, but it's a whole lot beefier than a 5-year-old laptop. And then Exhibit was a system that we built that utilized the only GPU option that Amazon EC2 has available. You get 22 gigs of RAM with that, 33.5 EC2 compute units, and it has 2 NVIDIA Tesla cards in it, which are very, very expensive GPU cards. Unfortunately, they're not optimized for doing password cracking. They're designed for doing things like financial modeling and very high-end things that require floating point mathematics that are not important for password cracking. So that's the only option they have available, and so that's what I utilized. If you're building your own box, you would not want to use those cards. Does anyone know what those cards actually run these days? I think they run probably around $2,000 or $3,000 a piece. When Amazon launched the service a couple years ago, they were substantially more expensive than that, but they're going to perform at in a less effective rate than a $500 card you can buy commercially. So do not buy an NVIDIA Tesla card for password cracking. The main tool that I utilized for this experiment was Hashcat Plus. I also used CryptoHaze Multi-Forcer, but it's a less flexible tool. One of the advantages of it was it is about 25% faster for doing its version of brute force attacking compared to Hashcat's version. And integrated within it, it has the capability of doing multi-node processing, so utilizing multiple distributed systems to collectively crack passwords. And at the time of this experiment, Hashcat Plus did not have that capability. It now has it for essentially AMD compatible, machines using AMD cards. So it has it for a different technology than NVIDIA utilizes. NVIDIA utilizes CUDA technology, and AMD cards do not utilize that technology. Hashcat Plus multi-node does not have that capability within it yet. So quickly, I'm going to run through some of the attack methods that I utilize. Combinator essentially takes one dictionary file and a second dictionary file and enumerates them in combination. So it takes one line from file 1, one line from file 2, and concatenates them to create a string. You could use the same dictionary file for both sides. So you could use dictionary file 1, dictionary file 1, dictionary file 1, and dictionary file 2. So if there are 1,000 entries in dictionary file 1 and 2,000 in dictionary file 2, that's going to work out to, I believe, 2 billion different combinations it's going to enumerate through. I could actually do straight dictionary attacks with the tool, but in my experience, those aren't very effective. So I did them. They didn't get me very good results, and they're probably not going to get you very good results either, because people tend not to use straight dictionary words these days. And so the combinator attack is going to get you more bang for the buck. A masking attack is a more granular version of a brute force attack. So a brute force attack just tries every single possible password combination in a particular key space. With a masking attack, you can do cool things like, let's say, as I mentioned earlier, that you suspect that users in your environment may capitalize the first letter of the string they use in their password. You could use a masking rule that says, I only want you to put an uppercase letter in position 1, and positions 2 through 7, I want you to use either uppercase letters, lowercase letters, or numbers. And for position 9, I want you to use special characters, and for position 10, I only want you to use an exclamation point. So it greatly reduces the key space that you're enumerating, which significantly reduces the amount of time to perform the attack. Now I'll show you an example of that later. With rules, you can specify a lot of things that you want to have done to a particular string. So you could take a dictionary and tell it, anytime you encounter the letter E, I want you to transform it into the number 3. So utilizing leet speak. I want you to take numbers and I want you to duplicate them. So if something ends in a 1, I want you to change it to 1, 1. I want you to strip characters out. I want you to reverse characters. So it allows you to perform various transformations. And there are tons of different transformations you can perform. With attacking, I'm going to demonstrate for you. I just utilize one of the base rule sets that Hashcat has built in, but I also build my own. And a hybrid attack is what you would think it would be. It's a combination of other attacking rules. And one of the hybrid attacks you can perform is to take a dictionary and then either prepend or append to it a masking rule. So if you had a dictionary and you knew that it's common for people to add 4-digit strings to the end because it might be a year, their date of birth, or the current year even, you could take the dictionary and append that, or you could prepend something at the beginning. So if you knew that first names are common to prepend to a different string, you can concatenate them together in that way. So by using these combinations of rules and then cycling through them more than one time, you can actually crack a high percentage of passwords. And to kind of let the cat out of the bag with eHarmony, I was able to crack more than half the passwords on a GPU machine in under an hour. Now, eHarmony did something stupid, something extremely stupid that made that much, much easier to do, which I'll show you in a few slides. So here's the process I go through. I define a sequence of jobs I want to run. By jobs, I really mean what kind of rules or attack types I want to perform. I then analyze the results both at the end of the run and during the run. I don't like to wait till the end of the run necessarily if the run's going to take a long time. So I don't want to run something for 8 hours and find out it was going to crack 0 passwords. So what I've done is I've created a bash script that checks every 15 seconds to see how many passwords have been cracked, at what frequency, and whether that frequency over that increment of time and overall is increasing, decreasing, going down to 0. So I can continue a run, or I can suspend it or terminate it based on how successful it is, or I can resume it at a later time. Then, so that allows me to eliminate or adjust jobs based on the results. But where it gets even more dynamic is I can create new dictionaries either during a run or after a run based on the output of other runs. So the output, what it looks like is the input's a hash file. The output's going to be a file that has a hash in it, and on the same line, it's going to have the plaintext password that was cracked. There's some other things you can have included in it too, like the hex version of that. It really depends on what your needs are. And then I rerun the jobs based on the new dictionaries I create and the new rules I determine will be beneficial. So a new dictionary may just be the passwords that I've cracked. So if I crack 500,000 passwords out of eHarmony, I may add those to my initial dictionary file, which can consist of dictionaries of English words, dictionaries of words from other languages, Klingon, anything that can be in a string you can find anywhere. So other password leaks are a really good source of password dictionaries. It's probably a little too small to see, but this is just an example of a bash script I have that does the heavy lifting. I actually utilize PHP to generate the bash script, but mostly I'm using bash scripts and text files to do the work. I'm using PHP and MySQL for some of what I do. Now, why PHP? Well, I started using PHP in 1999 after I got sick of Perl. Then I moved on to some other languages. I'm no longer actively a programmer, but I still do programming for projects like this. And it's the scripting language that I'm best at besides Bash. So it's what I use. So I recommend utilizing what you like and what you know versus what somebody tells you is best. If I knew Ruby or something else a lot better, that's probably what I'd be using. In terms of the syntax, here's what the syntax looks like for a Hashcat Plus. The first line is just the executable. The second line is the attack mode. In this case, it's a masking attack. The -m parameter with a value of 0 just tells it, I want you to try to crack MD5 hashes, not some other type of hash. And then I have a mask in place. So there are up to 4 parameters that you can specify. I specified 2, -1 and -2. So the first one has a placeholder of question mark lowercase u, question mark lowercase l. The u means only try uppercase letters, and the l means only try lowercase letters. So it's saying wherever you see a -1, well, a question mark 1 below, I want you to substitute all attempts for all uppercase letters and lowercase letters in that position. And so -2, the D means decimals or numbers 0 through 9. So what I'm telling it to do with this mask attack is try all strings that begin with I love and are followed by 1, 2, 3, 4, 5 either uppercase or lowercase letters, followed by a digit that's 0 to 9. So the reason I chose I love was, at this point, I'd already cracked a lot of passwords that were in the eHarmony database, and I had stripped off all but the first X characters of the passwords I cracked. So I started with 4-character strings, then 5-character strings, then 6, then 7, then 8. And then I sorted them for uniqueness and then put them in order of frequency. And I love was one that came up a lot. There were hundreds of passwords that began with I love. So I decided it was a good idea to add both I love to my dictionary and utilize it in a masking attack by adding additional strings to it to crack even more passwords. And I had really good success with that. And the -o parameter just tells it if you want to output the cracked passwords, which file you want to have those put in. You don't actually have to save them to a file, though if you want to have them just scrolling up and down your screen, you can do that, but it's not going to be very usable if it's a very long list. Any questions at this point? Okay. All right, looking at the time, I'm actually going to have to move through this a little bit faster. So TASH-WIO. So these are actually the most common 4, 5, 6, 7 letters to begin words in the English language. So I utilize that instead of performing a masking attack that involves every single word beginning with every single letter. If I have a limited time, I would do things like only look at strings that begin with these letters because they're most common. And though there are 26 letters in English language, 62% of words in English language begin with these 7 letters. And these are the frequencies associated with them. Okay. So when you run out of processing power, you have to split the workload across multiple machines. And there's 2 different ways you can do it. You can split the hash file so that you have multiple machines, each looking at subsets of a hash file. Or you can split the password candidate so that every single machine is looking at the same hash file, but looking at different subsets of the key space. Which do you think would be most effective? Splitting the hash file? Okay. Does anyone have a different guess? Or was only one other guess? Anyone want to, what's that? Password candidates. Well, it turns out that splitting of the password candidates is actually more effective. And that's because these software applications are so efficient at enumerating the hash file that that's not what is taking up a lot of the processing time. What's taking up the time is actually generating the passwords to crack. So you can see if we have a password hash file of 1 million hashes, for one of the tests I performed, it took 833 seconds. If I cut it down by 90%, so it was 1/10 of the size, it only reduced it to 742 seconds. So splitting it up into 10 subcomponents only would have reduced the duration for each by a factor of 11%, so 89% total. So it would not be a very efficient way of doing it. The better way is to actually split up the key space. So that's what I did. So I'm going to skip over some of these, but these are examples of some of the jobs that I ran. And they started off with a batch of mine just called batch number 3. So the first thing I did was I tried all uppercase and lowercase strings that were 5 characters long, got 14,000 matches. That took 19 seconds on the GPU box. You can see how many strings per second it processed and how many strings total it processed associated with that job. And the same results apply for the other tests that I did. And after these first 5 tests, I had cracked 195,000 unique matches. So one thing I want to point out is that during this testing, I did not remove hashes that had been cracked from my input file. I did that just to be able to demonstrate that some of these rules are not mutually exclusive. Key spaces can overlap depending on how you craft them. So you may end up cracking the same passwords over and over. So you would normally want to remove the cracked passwords from your input file. But as we saw on the previous slide, it's not going to really reduce the time it takes to perform the cracking that much. But if you want to reduce the time, that's the way you'd want to do it. All right, so here's where it gets interesting. So on job number 6, I tried 5 uppercase characters followed by a special character, got no matches, which made me think Maybe there are no special characters in the passwords that were dumped for eHarmony. And so from that point on, I decided not to try special characters because they didn't appear to provide me any value. So I moved on to some strings that had uppercase and lowercase. And what I noticed was by comparing one of the jobs on an automated fashion I already ran to one of the ones from this set, it appeared that there weren't any lowercase letters in any of the cracked passwords. And that's because eHarmony did something really stupid. What they did was, when you created a password, they converted it to uppercase before they hashed it. And so that doesn't actually reduce the time to crack by 50%. It reduces it by many, many magnitudes because it's factors of 2. So instead of 26 to the n passwords that you have to crack, 52 to the n, if you're just looking at letters, it's 26 to the n. So for, I think it's an 8-character string, it reduces it by a factor of 1/128th. So it made a huge difference. So from that point on, I didn't do any cracking involving lowercase letters. So you can see I did some other things, and these were all masking attacks. And at the end, I had 379,000 matched passwords. I did some more matching where masking attacks where I looked at certain first letters only. And you can see if I started with a T, I cracked more passwords than if I started with an X. And the number of passwords that were cracked corresponded pretty well to the frequencies that you would find in words in the English language. So take advantage of that. If you're working with passwords from different languages, the frequencies will be a little bit different. So people are predictable. You already knew that.
I have a question.
Yes?
So if they had converted them all to uppercase, how do you know that you've actually gotten their password?
Okay, so what I did is I ended up, when I figured that out, I ended up converting my dictionaries to uppercase because there was no point. So let's say your password was Apple, capital A, lowercase p, lowercase L, lowercase e. When you entered that or created that with eHarmony, they converted it to all uppercase, and then they hashed that. So from that point on, I was only testing the uppercase version. So when I tested all uppercase letters Apple and then hashed it and came up with a hash string and then looked it up to see if it was in the 1 million strings that I was processing and found a match, I knew your password was Apple. Now what I don't know is whether initially you created it all uppercase, lowercase, or some variation thereof. It doesn't really matter though, because if yours was all uppercase and his was all lowercase, when they converted it and created a hash of it, the hash was going to be exactly the same for the two of you.
Even when they were checking your password, no matter how you mentioned it, it was always
yes, yes. So my belief is they probably did that for usability purposes. That's not all that uncommon for organizations to do because people hit caps lock or they forget which letter they capitalized when they created their password months ago. And then they get frustrated and they contact the customer support or help desk. And so some organizations decide to make things easy by doing that, but they won't tell you that. So they're making your password less secure when they do that. Okay, so then I moved on to the rules, and the rule set I used was called Best 64. It's a list of 64 rules that Hashcat has in place that you can leverage. And you can see at the end of that, I had matched 540,000 total unique passwords. Not too bad. That was less than an hour of processing time. Then I did some of the combinator attacks where I took one dictionary and matched it up with another and created a string and then hashed it and tested whether it was a match. And then I did the hybrid attacks. At the point I did the hybrid attacks, I looked at the output from all the password cracking I'd done and made a new dictionary that included those new cracked passwords. I used all those dictionaries, which consisted of leaked passwords from other attacks. There were about 1 million passwords total. Top passwords from the RockYou leak, English dictionaries, list of first names, list of last names, things like that are easy to find and build, and ran these attacks. And then I was up to 69% matches. Then I started doing some things that took a lot of processing time and didn't really provide a lot of value, but I wanted to show you that anyway. Show you there's things you can do that when you get to a certain point, it's going to take longer for each incremental password to be cracked because the key space is going to be longer. or larger, I should say. So I ran a few more jobs, and so here's some masking attacks with really long strings and really big key spaces. In the end, I had cracked 76% of the passwords. So if we look at each batch of jobs, here's what it looks like. And you can see some of the jobs perform the cracking at different rates than others. So pretty fast, 582 million strings per second, all the way down to almost 1.7 billion per second. You see some that are pretty slow. I don't have time to really go into that, but it has to do with how efficiently the GPU could be utilized by the software. And so with the brute force-like attacks with big key spaces, you're going to get a lot closer to this type of rate than with some other attacks. So on average, it was about 1.2 billion strings per second. So you really don't want to use MD5 though. What you want to use is you want to use Bcrypt or PBK DF2. These are hashing algorithms that are designed to take a lot of time to run, and they have a workload factor, which essentially is something that as processing power gets faster, the workload can be increased so that instead of billions of hash attempts per second, you can adjust these algorithms to take however long you want on the computing hardware you have. So if you want it to take half a second for a single hash to be generated, you can do that. And from a password generation and password lookup perspective, it's not going to bother your users, but it's going to really make it harder for the black hats to crack the passwords. And these particular hashing algorithms, because they're not highly repetitive, and GPUs rely on efficiencies by performing highly repetitive tasks, they're not very efficient on GPUs, so they may actually be, in some cases, slower than running on a CPU. So in terms of total cost, running the full set of jobs cost $18.90, but I cracked 54% of them for $2.10. So unless your budget is like under $3 for this particular set of password hashes, there wouldn't be a reason to build your own machine, because you're not going to build a machine for under $3, and no one has a $3 budget. Now, if they hadn't converted them all to uppercase or things were different, it would take more time and be more expensive. But for the kind of work I do, my goal is not to crack 100% of the passwords. My goal is to crack a fairly decent percentage to make a case for why something needs to change, either user behavior or technical controls or something. So I don't need to crack 99% of the passwords. 10% may be enough for what I'm attempting to do, and it may be enough for what you're trying to do. Okay, just a little bit of a rant of mine. A lot of people in the field say, oh, cloud's terrible, cloud sucks. Can't touch it, can't feel it, don't have control over it. And to some degree that's true, but the cloud's coming in your environment like it or not. So what I suggest is give it a try. If you haven't used it, try something like EC2. And that way when you're talking to the CIO or CEO and you're ranting about how bad cloud is, and when they ask you, well, have you done cloud, you don't have to say, well, no, I haven't, it just sucks. Okay, so spot instances is where it gets really cool, and that's where you can bid on excess capacity that Amazon has. And so in this particular case for a GPU box, you can see they actually show me in the bottom middle left that it actually costs around 35 cents per hour for their available excess capacity. I bid 55 cents per hour. They would only charge me what the going rate is. So if I bid 55 cents and the going rate's 35, they only charge me 35 cents. I can tell them I want one machine or I want 10. I can tell them that only give me those 10 if all 10 are available, or give me as many as you have up to 10. And here's the time frame on the calendar that I want this offer to be good for. So by doing this and utilizing the startup scripts, I can fire this up and tell it that I have a master node and I want it to have all the child nodes communicate with it. And instead of costing me $2.10, it costs me 35 cents per hour. So I can get 6 or 7 machines for the price of one. The downside is I'm not guaranteed that spot instances will be available, and I'm not guaranteed how long they'll be available after I start them up, which are really bad if you're hosting a website. It's not bad if you're doing password cracking. Just a screenshot from CryptoHaze Multi-Forcer. This is a version where I had one machine with 2 GPUs in it and a couple, 2 or 3 other machines that were reporting into it. So the key space was being distributed across it via masking attack. You can see that some passwords are cracked. In this particular case, I wasn't using the ERMe database. I was using a test database that came with CryptoHaze. What I ended up doing was rolling my own with Hashcat Plus to do the work and pass the key space subsets over to the child nodes. In terms of the speed, the exhibit box was my single GPU box, and it was able to crack around 1.6 billion passwords per second. Yoda was the CPU version that I set up on Amazon EC2. Still pretty fast, 6.2 million passwords per second, but magnitude slower than Exhibit, or Exhibit's magnitude's faster. So in fact, Exhibit is 258 times as fast as the CPU machine. So Exhibit costs $2.10 per hour. Yoda costs 32 cents per hour, but an hour of compute time on Exhibit would have been equivalent to 258 hours on the CPU machine. So, and it didn't cost 258 times more to utilize that service. So it was 3,831% more expensive to use a CPU machine than the GPU. So I would never use a CPU machine on Amazon EC2 for password cracking unless my budget was under $2.10, which it's never going to be. Okay. So I haven't talked at all about passphrases, and I wanted to look to see were there passphrase dictionaries out there, and I'm close to done. It's only taking me a few more minutes. I just want to hit the basics. And
We're at dinner time anyway, so keep going.
Keep going? Okay.
Yeah, not interrupting anybody else, so all good.
All right. If any of you are too hungry, you can leave, and it won't hurt my feelings. I'm going to be around all weekend, so if anyone has any questions after this presentation or anytime this weekend, just grab me. But I was curious whether there was a passphrase. You have a question now?
I was going to ask, I know you had been using, like you said, your Bcrypt for when you're looking at the output of your, like the plain text versions of the package that you crack. Have you looked at some of the script pronunciation, like PPAL or People by Robin Wood?
I have, yeah. So I've utilized that to look at the frequency. I'd already rolled my own version of a similar tool that does more than his, but is more poorly written. And I built that when I did my testing of RockYou back in like 2009, 2010. That's a really great tool. So yeah, that's a great tool that's out there. It's free, it's open source, and it does things like allow you to analyze the output file for letter frequency and length and that type of thing. So yeah, I kind of rolled my own. I would have used his because it's better, but it's written in a language that I'm not very proficient in. Do you have experience with that? Have you used that and had good success with it? Right. Yeah, so that's a really good point, is by stringing some of these available tools together, you really don't need to roll your own. You can string some of these together and utilize rule sets other people created, and so you're not reinventing the wheel. Eventually, as you become a proficient, you're going to want to probably tweak those so it performs better in your environment or with the particular file set you're working with. So I looked for a passphrase dictionary. I could never find one. Has anyone ever come across a passphrase dictionary? Because if you have, I'd like to be pointed to it. You've seen one? You have one. Great. We should talk at some point. Or not. Okay, so I couldn't. Yeah, 5 entries. So I have one with 5 entries too. So I couldn't find one, so I decided I was going to build my own, or at least I was going to try to build my own. So passphrases are essentially sentences or strings of words, or you can use mnemonics, which could be something like taking all the first letters from a string of words and creating a passphrase based on that, and then you can do transformations to those. So that's what I attempted to do. But where are you going to find passphrases? There's no dictionary. I tried looking at leaked password files. Well, he has one. Yes?
The simple version, the starter point, is all of the popular phrases in IMDb. Everything from all the movies. Start there.
That's really good. So that's a good segue into something I was going to say, unless I remove the slide. So you could crowdsource it by asking people, well, who's going to tell you their passphrase. You can ask organizations to share theirs with you. I actually worked in an organization until 2.5 months ago, and I actually implemented passphrases, but then I left, and so now I'm not in a position to ask them for their passphrases. Nor should they give them to me. You can wait till they've been leaked, but not many people are utilizing the passphrases, so the databases of leaked passwords are not going to have many in them. Or you can build your own. So you can do something like start with IMDb and look at things like movie titles, character names, and that type of thing. Or you can get creative. So some of the things that I did was I decided, where can I find things that might constitute something somebody would use for a passphrase? So I looked at ebooks, and I pulled in a bunch of ebooks, converted them into text. I looked at movie scripts, and there's a lot of those available. Song lyrics, tweets, status updates on Facebook, basically anything that I could find in a file format that I thought might have strings in it that could potentially be something somebody would use as a passphrase or base a passphrase on. I pulled all that together and I did some analysis, and I wrote a set of scripts that do a bunch of things, and it's not really too important what they do. Kind of get to the conclusion. And so essentially what the output looked like is I did it two different ways. I tried to delineate what a sentence was by looking at things like punctuation, and look at what appeared to be a sentence. And then I converted them all to lowercase. I pulled out some strings, and then I created the mnemonics off of it to create acronyms. So if I came across a sentence like a person who never made a mistake, never try anything new, converted it all to lowercase, created the acronym based on it. Then I started looking at subsets of consecutive words to make new passphrases. And then I did it a separate way where I didn't care whether there was punctuation or not. If there were consecutive words, I just called it a passphrase. And I made a really big database, and then I made dictionaries out of that, and I performed testing. Now, unfortunately, there's nothing really good for me to test against to know how effective my passphrases are. And that's the crux of my problem. I feel like I have some pretty good passphrases because I was looking at things like frequency with which they appeared in Google and frequency within which they appeared in my file sets. Well, I have nothing really good to compare them against. So if any of you happen to have real passphrases in databases that you can share in some format or know where some of us can find them, I think that'd be really helpful for us to continue this kind of research. And just to wrap things up, this is what I hoped you were going to get out of the presentation, and covered all those things. Just quickly, in terms of buy or rent, there is no right answer for that. It really depends on what your particular business case is. If you're going to do a lot of password cracking, you may want to build your own machine. If you're going to do very little, use something like Amazon EC2. That's it. So again, if anyone has any questions afterwards or anytime this weekend, just let me know. Or if any of you have any ideas about how I can do this differently, I'd love to hear how you're doing this successfully, or other types of research that could be performed. I'd love to consider that. So thank you.
Guys, we got food, free drinks next door. Come on over and join us. One question.
Yeah.
If you do a spot install and terminate before you get back to it, can you still get your data, or is that something you're piping out regularly?
No, you cannot, but I should say I've never had that happen for me while using GPU boxes. So, but yeah, I believe they only terminate the end of an hour. So if you were dumping your data or transferring it to a centralized system before the end of the hour, that should never happen to you. But again, since the data that I'm moving back and forth is so small, and internally moving data between machines, I mean, we're talking about a second to move the data. For me, it's not a problem. But yeah, if you were running something very long and you didn't move the data, that would not be a good idea. And during my initial testing, I made that mistake. I accidentally terminated a machine when I meant to stop it. And I learned my lesson the hard way.
Just upload S3 every hour or every half hour.
I'm sorry?
Just upload S3 every hour or every half hour.
Right, yeah, you can definitely do that.
You're just blasting through them, right? You're not going to do the same query again. So,
Right.
and just assign really short time to live on S3. And maybe, just keep expiring any key which is not your latest, any replica.
Right. So you can do that. You can definitely build some more granularity into it. What I typically do is craft it so all my jobs are going to take less than an hour.
Oh, okay.
So it's less of a problem that way. But yeah, so if you want to do that, you can. And you can mount additional storage if you need it to any of the instances. So if you need more storage, that's always a possibility.
You were, well, because EBS would survive, right?
Right.
So you could, yeah, even if you take away your machine, EBS would survive, maybe slightly consistent. But
Right, and the storage is very inexpensive.